All right. Well, good morning again. We are flying along. I think today is going to actually be really short. One of them is just finishing off chapter 10, and then the other is on 11.1. And I think a lot of that, I'm just going to do a very basic introduction because it's kind of a repeat of what we did before. It's just rephrased in a slightly different form. So instead of me droning on and on, I'll probably just do a couple examples and let you work on that, and then we can handle it tomorrow if you have questions. So I guess 10.3 and 10.4 are due today. So I think that's dot and cross product. Yeah, so let's see, right? So 10.3, 10.4 homework is due today. And then 10.5 yesterday, that was on lines. And that was in lines in 3D. And just as a sort of reminder, you could either write it as vector form, where it's kind of like the x1 coordinate plus some multiple of like the run. So if you want to call that like d1. And then in the y component, it's whatever the base point is, the y component of that coordinate, plus whatever multiple of the rise there is. And I'm using d's just because we used it as a direction. And then we have z1 plus whatever multiple of v3. And so that's one condensed form of the vector format for a line. So the direction vector is given as d1, d2, d3, and any base point on the line. So any point you want on the line can be put in for x1, y1, z1. So, you know, maybe pick an easy one to use for that. So that's a mess. So you have your direction vector. You take every single multiple of that direction vector, small, big, you add it onto your base point in both directions, and that'll give you the entire line. And then the other two were just to do the parametric form, which says, let's just take x, y, z, the variables, and just write out each piece. And that's really it. So x1 plus t times d1, and then y1 plus t times d2, and then z1 plus t times d3. Then you have to write all three of those together. So it's like a set of equations to get the line. If you don't want to do that, and this is one where it takes a little while to figure out, but once you get the symmetric one, you're like, oh yeah, that's a little bit more condensed. It's a series of like two equalities. Everything is equal. So instead of writing a bunch of equalities, we just write one chain of them. And so the answer is, well, I just take and solve for t in each one and then set all those three t's equal to each other because they're the same. So x minus x1 divided by d1, just subtract over. So y minus y1 over d2, and y or z minus z1 over d3. Now you do have to make sure that the d1 is not 0, d2 is not 0, d3 is not 0. And anytime any of those are 0, you just write it off to the side as a separate equation. Like if d1 was 0, you know, for example, if d1 was 0, then you couldn't write this because you'd be dividing by 0. So instead, you just say, well, if d1 is 0, that means x is always equal to x1. And that's actually was in the example we did yesterday. So you might have one set of equations. You might have, you know, one little variable's off on their own, and then the other two are equal, or who knows? I mean, yeah, I think that's probably about it. You don't want to have more than, let's see, 0, 0. I guess you could have like 0, 0, and then you could have 1. So you wouldn't even want to write the symmetric form. But that would be like a straight up. So I guess you could do that. Anyway, symmetric's nice if all the d's are non-zero, and otherwise you can use any of these forms. So you're like, well, why can't I just do y equals mx plus b? And the answer is in the last section of the book, 10.6, is on planes, not airplanes, but you know, so a plane is just, you know, here's 3D, So a plane is any 2D flat surface that goes through there, and it kind of can be difficult to draw, so we usually just sort of slant them. They go in all directions, but we usually just draw a square or a rectangle. And so what we want to do is try and figure out what the equation of a plane is. And we draw it over here again, so the axis is on the way. The key is, in order to do this, you need two things. And one of them is a base point. So we need any point in the plane to get us started. We call that P and Q over and over and over. Sorry about that, but I don't want to introduce a ton of letters. So I have any point in the plane, and so there's P. And then the key is, it's interesting, but what you need is you need a vector that points perpendicular to that in all directions. So you need a normal vector. So you need a base point and you need a normal vector. And so that'll be, I don't know, ABC. I think the book uses ABC. I suppose you could use N1, N2, N3, whatever you want. A. So that just means it's a vector that points perpendicular to the plane. So that means that if I took any point in the plane, so for any other point, call it X, Y, Z, that's where we're going to get our variables from. What does it mean to be normal? That means it's perpendicular. Well, how do you test to see something perpendicular? It turns out that we did that before. We know that, let's see, vectors are perpendicular if the dot product is equal to 0. So that's the key there. So what we're going to do is we're going to take the vector between P and this other point. We're going to do the dot product with the normal, and we better get 0. So we'll call this other point. And again, sometimes they use P and Q. Well, they use P and Q a lot, so we'll go ahead and call this one Q as well. So any other point in the plane Q, which is just an X, Y, Z, that means that the vector from P to Q, so that's going to be a vector that's in the plane somewhere, then we need PQ to be perpendicular to N. Because again, that's the definition of N. It's everything, it's a vector that's perpendicular to any other vector that's in the plane. So if you convert this out, and you look at PQ, then you'll end up getting the vector X minus X1, Y minus Y1, and Z minus Z1. So that's the vector PQ. It might be QP, but it's a vector that's in the plane. And I'm going to dot that with ABC. So there's PQ, here's N, and that better be equal to 0. Because that's the definition of perpendicular, or that's the property we found. So here's the equation. Just do this dot product. How do you do dot products? It's the first one in the first vector times the first one in the second vector added to the product of the second one with the second one, and then added to the third component of the first, third component of the second. And you add them all up. So you get a very simple formula, A times X minus X1. So it's the first two multiplied together. You just put the A in front. Plus B times Y minus Y1 plus C times X minus, or Z, right, Z minus Z1 equals 0. And that right there is the equation of the plane, called the standard form equation for a plane. So it kind of looks like Y equals mx plus b. You could solve for z, and you'd have x's and y's in it. But you have, really, you have two variables that you could pick, and you can get the third one. So it's like two independent variables and one dependent variable, which means I can go one direction or I can go the other direction, but then z is fixed. at that point, so you can't then go up. So that's why it's flat. So it's like a 2D thing inside of a 3D object.
Sir, I have a question. So when we did dot product yesterday, where we put the numbers on top of each other, and then if it was I, we we did the J's and the K's cross multiplied. That was dot product, but
That's
this
cross.
is
That's cross
oh,
product.
that's cross product. Sorry.
Yeah, that's okay. Yeah, we'll do some homework questions here shortly, I think. But let's do some examples of this. I mean, even just to get a feel for it again. So, for example, if we said, find the plane that contains the point, and we'll just go with one of my favorite ones first. 1 minus 1 1 with the normal vector. And you can pick whatever you want. Say 1, 2, 3. Right. So I don't know exactly what it looks like. All I know is that it has the point 1 minus 1 1. And then if I drew a vector, if I drew the normal vector, that means it has the point perpendicular. And I've drawn it this way, but it's like perpendicular in all directions. So that's the vector 1, 2, 3. Then in this case, you just use the standard form. And that the components 1, 2, 3 are the numbers in front. So it's 1 times something, 2 times something, 3 times something. I don't have to go through the whole dot product again. I can just use the standard form equation. And so it's D1, D2, D3, or A, B, C, or whatever letters you want to use. And then we'll have x minus the x component, so that's x minus 1. Y minus the y component, so that's y minus a minus 1. And then z minus the z component of the base point. And boom, you end up getting your standard form equation for a plane. So again, it kind of looks like point slope form for a line, except everything's been moved to the left, and instead of doing like, slope, you've got like run, rise, and depth, and then you've got x minus the x coordinate, y minus the y coordinate, z minus z coordinate. That's kind of the same. So that's one. Now, you can easily just multiply everything out because it looks a little cluttered. So if I did that, I'll just sort of multiply out here. We'll have x minus 1, 2y, so distribute the 2. This will be a plus, so that's plus 2. And then this one here, 3z minus 3 equals 0. And so if I put all the numbers on one side and all the variables on the other, I'd have x plus 2y plus 3z equals, let's see, we've got minus 1, minus 3. So minus 4 plus 2 is minus 2. Bring it to the other side, we'll get plus 2. So just bring the numbers to the right and leave everything else the same. So this is another form of the plane. It's not standard forms, but you can at least still see the direction vector, 1, 2, 3. That'll be the normal vector that comes off of the plane. And then what's the base point? Well, it doesn't matter what the base point, it can be any point that satisfies that equation. So if we just for kicks, wanted to work backwards, find, 3 more points in the plane. Well, all that means is we just have to find x, y, and z that satisfy that equation, satisfy the equation of the plane. So we could try, let's see, if x was 1 and y was 1, then that would mean that z would have to be, well, we just come up here and figure out what z would be. So if x is 1, this is 1. If y is 1, this is 2, so that'll be 3. So that means that if we subtract them, maybe I'm doing too much in my head here. So if I just took these and substituted them in, I'd get 1 plus 2 plus 3z has to be 2. So that means that I can cancel the 2's and bring the 1 over. That means that z has to be negative 1/3. So that means that the point 1, 1, minus 1 is in the plane. So any point that satisfies all of this condition here, that 1x plus 2y plus 3z equals 2, that'll give me a point in the plane. So I ran out of room there. Maybe let me just do it by inspection here. Here's an easy one. Let's try this. What about if x and y are 0? If x is 0 and y is 0, then that means that z is going to have to be 2/3. Just by solving this equation. 0, 0, 3z equals 2. So there's that. I could set x and z to be 0. If x is 0, then if z is 0, then we just have 2y equals 2. So y is equal to 1. And how about the last one here? If we set y and z to be 0, so if y is 0 and z is 0, then x would be 2. Okay. So there are 3 more points that are in the plane. And the reason why I drew these is because if I take these are actually the intercepts. It's the axis intercepts. And I know I'm sort of going down and jumping back around. But if I wanted to actually plot this as doing x, y, z, then I could plot those 3 points. So 0, 0, 2/3. 2/3. I could go 0, 1, 0, so that means that y is 1. And I could go 2, 0, 0, so come out here on the x-axis. 1, 2 units out, and that's 2 for x. And that means that just like before, 3 points determine a plane, well, or sorry, 2 points determine a line, well, 3 points determine a plane. So it has to pass through those 3 points. We'll try and extend it like that. Got to contain that triangle, and it's sort of slanted that direction. And again, if I pointed the normal away from it, it would point 1 unit for x, 2 units for y, and 3 units for z. And I can get that normal. So that's sort of approximately how I might do that. If I knew the point and I knew the normal vector, I could just plug straight into the standard form. So what happens if you don't have that? Well, we might have to go back and combine some things we had. So let's try this. So find the plane that contains points 0, 0, 0. So it goes through the origin. It contains 1, 2, 3. Okay, now we got to put another one in there. Minus 2, 3, 3. So create the plane that passes through those points. And you're like, that's not fair because you told me I need a point and a normal. And I've got a point, I got 3 points, but I don't have the normal. So I need the normal vector that points away from the plane. So now you got to go back and see the homework that you basically just did and think about what's going on. That if I have these 3 points, maybe I'll just call them P, Q, and R. Then I've got my point P, I've got my point Q, and I've got my point R. And I know that they're in the plane. And I need a vector that points away from the plane. If you get used to this sort of thing in your head, looking at like right-hand rule and stuff, this is a suggestion that in order to get something that's perpendicular, you want to do the cross product. So if I have the vectors PQ and I have the vector PR, and if I took the cross product of those, I would end up with the vector PQ cross PR. And the whole point of cross products is it creates something that's perpendicular. So that's what we're going to use. The cross product is always perpendicular to the two vectors it started with. And if it's perpendicular to one and perpendicular to the other, then it's going to have to be perpendicular to the entire thing. And that will be my end. So now we're using the cross product to go back and construct the plane. So if that makes sense to you, then we need to calculate out what this is. So let's see, I need the vector PQ, and that goes from P to Q. So it's pretty easy when you start at the origin. Going from the origin to there, I need to put 1 in the x component of the vector, 2 and 3. And PR, well, that's the vector minus 2, minus 2, 3, 3. So from P to R, I got to subtract 2, add 3, and add 3. So that gives me that. So in order to get N, I need the cross product of those two things. And now, this is maybe good practice anyway for the homework. That's where I do this I, J, K, and little subdeterminants and stuff. So 1, 2, 3, minus 2, 3, 3. And I got to work all that stuff out, maybe just for practice. I know I'm going to have in the I direction, maybe skipping just slightly. In the I direction, if you kind of eyeball it and cross it out, you've got 2, 3, 3, 3. So you're doing this little subdeterminant down here. So it'll be 2 times 3 and 3 times 3, and then you subtract. So that'll be 2 times 3 minus 3 times 3. So that'll be minus 3x. And then for J, it's got a built-in negative sign. So J, I cross out the J stuff, I'll have 1, 3, and minus 2, 2. So I do 1 and 3, and I do 3 and minus 2, and I subtract. So it's 3 minus a minus 6, so that'll be 9. And with the minus, that gives me minus 9. And then the same thing for K. So for K, it has a plus, and we do a little subdeterminant. It'll be this one down here. So 1 and 3, 2 and 2, get the signs right. So 3 minus and minus 4. So 3 plus 4 is 7. So that gives me 7 total. And so that's my normal. So I have 3 points. You can pick any point you want for the equation. Probably P is the easiest. And then that's the normal. So if I use the base point, P, 0, 0, 0, and I use this normal vector, then the equation of the plane will be negative 3 x minus 0. So it's the, I'm use the first part of the normal and the base part. Minus 9 times y minus 0, and then plus 7 times z minus 0 equals 0. And I guess if you clean that up, see if I can stick it in here. Minus 3x minus 9y plus 7z is 0. Maybe down there at the bottom. And I write my 7s like that. So there you go. And you can easily verify that these points back up at the top, Q and R, are in that plane by just plugging them in. Plug in 1, 2, 3. Do I get 0? Well, let's see, if I plug in 1, I'll get negative 3. If I plug in 2, I get negative 18. Put those together, that'll be negative 21. But when I plug in 3 for Z, I get a positive 21. So that all cancels out to get 0. And the same thing for the last one. Negative 2 goes in to give me 6. 3 goes in to give me minus 27. So that's minus 21. Again, plug in 3 for Z. Boom. And I'll get 21 minus 21, which is 0. So it's a nice little verification that I got it. Okay. One more example, and then we'll do a distance formula and then see if you have questions on the homework. So they might say something like this. Well, find, now this ties the last two sections, this last section and this section together. Find the plane that contains with lines, these two lines, and these are given in vector format here. So line 1 is 2 plus t, 1 plus 2t, 2 plus 3t, and line 2 is 2 plus 2t, 1 plus 5t, and 2 plus 4t. So if you're not quite as comfortable with the equations of these lines given in these formats, I think this question may help. So there's a couple ways to go about it. There's the shortcut once you see it, but I think it's hard to see. So I need to find, so let me just draw this real quick. So we have a plane, and then we have one line that goes this direction, and we have another line. And I don't know exactly if they're parallel or if they cross, but I think they cross. So they're inside the plane. And so what I need is 3 points in order to go back to the one that I just did. If I had 3 points in the plane, then I can do my cross product again and work it through. And maybe that's the easiest way to do it. So I need 3 points on there. And now one thing to notice is you've got 2 and 1 and 2. You're like, oh, look at that. They both have the same base point. So I know that 1 point is 2, 1, 2. And you could get this by setting t to be 0 in either L1 or L2. And you'll get 2, 1, 2. That's one way to get a point. How do you get other points? Well, you can just plug in different values of t, and that will give you different values. So if I set t, if I set t to be 1 in L1, then I would get the point, and I'll call it Q, plug t equals 1 in. So this would be 3, 3, and 5. So 3, 3, 5 is another point in the plane because it contains the entire line. So if I find a point on the line, that has to be in the plane too. Pick another value. Well, I don't want to pick another value along L. I don't want everything to be in a straight line to do the cross product. That would be bad. I get 0. Any two vectors that point in the same direction across them, I'll get 0. So let's do it in L2. If I plug in t equals 1 into the second one, I'll get 2 plus 4, 6, 6. And now I'm back to the previous problem. I've got 3 points, so I just follow that process. So like in the last example, the normal vector will be PQ cross PR. And then once I have this normal, I just plug those points in and I'll get the plane using the standard form. So I need to do this cross product. So let's see, what's PQ and what is PR? Well, let's see, in order to go from P to Q, I have to add 1 for X, I gotta add 2 for Y, and I gotta add 3 for Z. 1, 2, 3. And to go from P to R, I have to add 2 for X, 5 for Y, and 4 for Z. So 2, 5. Now, as you work these problems through, you might be like, wait a second, 1, 2, 3, that's exactly the numbers that are on the T's for the first line, and 2, 5, 4 is exactly the ones that are on the T's for this. So it actually turns out that if you knew the direction 1 vector and you knew the direction 2 vector, then you could have actually just crossed those together to get N, and that's exactly what I ended up doing. This is B1 and this is B2. So these patterns start to emerge Uh, but anyway, that's if the lines cross. If the lines don't cross, then games, yeah, you're gonna have to figure out something else. So I got to cross those together, and maybe you could work that out, but I'll just tell you what the answer is on that one. It's a -7, 2, and 1. So you can do your matrix out and figure out all these points, and this is what it ends up being. So that means that the equation in between, using the standard form, will be -7 times something, 2 times something, and 1 times something equals 0, because that's the pieces of the normal. And then what goes inside is like x minus the x coordinate, y minus the y coordinate, z minus the z coordinate. And you can pick any point you want. If I use p, so we're starting with p, so with p, that would be x minus 2, y minus 1, and z minus 2 as well. So just take the x, y, and z coordinates and here's my equation. I guess if you want to multiply it out, you can. I think it's a little bit easier if you leave it like this, because then you can see the normal right off the bat. That's the first numbers. And then you can see one of the base points right off the bat as well. If you multiply all this out and move it to the other side, you can still see the normal, but you have to go back in and find the base point. And that's not hard, but it's a little bit easier just to read it off of a nice form like this. So before there's one last thing to do in that section, but let me just go ahead and break and see if you guys have homework questions on 10 on the previous two sections. I guess not.
So I guess I was just a little confused on when you dot them and when you multiply the vectors. When do you do which? And
Well, yeah, the word multiply anymore, we don't really use that for vectors. We just use the word product, and there are two products. One is dot, and one is cross. And the questions will be find the dot product or find the cross product of these vectors. So it'll be just straight up. It'll say find v dot w, and you'll end up getting a number answer for scaling. Answer. And then if you do v cross w, you'll end up with a vector answer. And what do they actually mean? Well, this vector here is perpendicular to both of the starting lines, v and w. So it's a way of creating this three-dimensional structure. If you knew v and you knew w, then the cross product would be your thumb. V and W are your like pointer fingers, and then this would be perpendicular to both of them. So it's a nice way of constructing sort of an axis system. So there's a lot of symbols on the board here, but basically this means that if you took V and dotted it with this new guy, you would get 0. So that combines it all together. The cross product is a vector, which I can then dot with any vector I want. And because they're perpendicular, the dot product will be 0. So that was a nice thing over there is if v dot w is 0, then that means that v is perpendicular to w. So it's possible that v and w are perpendicular, and then when you cross it, you get a third one that's perpendicular to both. So it's kind of like the XYZ axis. Other properties in there is you can find the angle between them, you can find lengths, you can find areas of parallelograms. So they have all sorts. I think we did an application before with, let's see, what was it, like the distance from a point to a line. We had a point on the line and a point off the line. and you wanted to know what this distance was, then it turns out that that distance is just, you take PQ, cross it with D, and divide by the length of D, and those are all vectors. Where D is the direction of the line. So that's just one more application of cross product that you can find distances in space. But, I mean, in general, if it says multiply these two vectors together, you'd be like, which one? Is it the dot product or is it the cross product? And they have a lot of pretty significant differences. I don't know if that answers your question or not.
Yes, it does, sir. That makes a lot of sense. Thank you.
Okay. Any specific questions on homework, or have you started looking at it?
Sir, can you go over problem 20 real quick on 10.3?
All right, so 20 says, it's a pretty good lead-in actually to what we just did. It says find, well, it says find two vectors, and I forgot to say the word, the word orthogonal and perpendicular mean the same thing. So it's a fancy term for perpendicular. And sometimes when you're trying to describe things in a map, you might say orthogonally, and the answer is that just means north, south, east, west, but not diagonally. Touching on the sides, but not diagonally. So find any vector that is perpendicular to this. And how many are there? Well, there are infinitely many, because basically what you're doing is this. Suppose this is V. This is the long answer. Sorry, I always give long answers, and my kids are like, get to the point. So here's V. If I found a vector that's perpendicular this way, and then I found a vector that's like perpendicular this way, and then I found a vector that's perpendicular that way, and I found a vector that's perpendicular to that way, and I put all those vectors together, it turns out I would get an entire plane of vectors, and V would actually turn out to be the normal, so it's exactly what we just did in this section. So any vector that's in this plane will work. So if you want, you could just find the plane and work backwards, but you didn't know that at that point. So all you need to do is say, well, what does it mean for a vector W to be orthogonal or perpendicular to V? Because that just means I got to do, we'll just call this like W1, W2, W3. I want to dot that with 1, minus 2, 3, and set it equal to 0. So perpendicular product is 0. So multiply this out, I'll get W1 minus 2W3 plus 3, or W2 plus 3W3. That has to be 0. Because I'm just multiplying out, doing the dot product, I get this. So I have 3 variables, like one equation, but 3 variables. So anytime you have one equation and 3 variables, that means that 2 of the variables will be independent. They can be any value they want. So I can just pick in 2 of the variables and then solve for the 3rd one, and then that will give me my answer for W. And to do the algebra nicely, it might be easier to just say pick values of W2 and W3, any values you want, and then W1 would automatically be just solve for W1. It would be 2W2 minus whatever 3W3 you put in there. So let's see, just put some examples here. I pick the W2 to be 1 and W3 to be 1, and that means that what is W1? Well, W1 would be 2 minus 3 would be minus 1. So that means one vector that works is minus 1, 1, 1. Okay. So that is one vector. And you can just check it by multiplying back through. I'll get minus 1, minus 2, and plus 3. That's a good deal. Maybe one more because it said to find 2. We could do 5, 10, W1 do? I'll just plug in 5, I plug in 10, I'll get 10 minus 30, so that's minus 20. So that's another vector that works. Minus 20, 5, and 10. Yeah, now one thing you probably don't want to do is, let me put a note here. I don't think you want to put W2 equal to 0 and W3 equal to 0, because then W1 would end up being 0. And technically it's true that, you know, we get the vector 0, 0, 0. It has no length, right? It's called the 0 vector. And we do need it sometimes for calculations, but if you're going to plot it, how do you do it? You can't. It's just a single point. When we're talking about perpendicular, you typically say everything, but don't use the 0 vector because it doesn't have a direction. 0 is annoying. It's kind of annoying. I like 0, but it's useful, but sometimes it just causes problems. Can't divide by it. This has no direction. You can't raise 0 to 0. 0 is useful, but it also causes problems. That's the long answer. Does that help?
Yes, sir.
Cool. Any others? Well, maybe while you're thinking about it, let me finish off 10.5. I know we've sort of typically coming up to a break, and we will. But this is not super long. We have a second distance formula. So we've already done one where it was a distance from a point to a line. Now this one to finish off the chapter is the distance from a point to a plane. So here's what I mean, is you've got a plane, again, stretching infinitely far out everywhere. You have a point that's not on the plane. And you guessed it, I'm going to call it Q. Lots of P's and Q's here in different contexts, so just be careful as to which one you're doing. And so what I want to do is I want to drop a perpendicular down and figure out what that distance is there. And we'll call it, how many letters here? I think the book might still call it H, it's like the height above that. But that's what we want to find, is the perpendicular distance from the point to a plane. And so there's a couple ways to do it, I'm pretty sure. We could do like an actual calculus minimization problem where we could find the distance from any arbitrary point and then minimize that distance. Shades of Calc 1 again. And we're all excited to return to. Instead, let's just use what we already have. If we take any point P, we take a point P in the plane. And if we put the normal vector there, I'm going to make it slightly long. It might be longer than it really is. But if I took PQ and I took the shadow over here, I took the shadow of that vector onto N, and it turns out that this length is exactly the same as this length over here. It's just, you get a nice little square going on here, or rectangle going on. So this distance will be the same as the top distance, and then the h's will be the same. Maybe slightly slanted, but this vector right here, and notice it's getting cluttered, but that vector right there is exactly the projection or the shadow of PQ onto N. It's that vector. So that means if I want to find H, I take the magnitude. take the length. And so H would be equal to the length of the projection vector EQ down onto N. You're like, gotta go back to section 3, find the projection vector, go through all that mess, then find the length of that. And that's technically true, but there's a little bit of algebra we can do here. So algebra magic. Just do as they say. Just kind of wave my hands, look over there, and then I'll put the answer in. And it turns out it's super nice. It condenses down to this. It's Q dotted with N, and that could be negative. So I take now this bars mean absolute value. That's absolute value there. And then I divide by the length of N. And so that is now my distance formula, not from a point to the line, that was before, this is from a point to the plane. So if I knew Q, I'd have to find P, I'd have to find N, and then I would just use this formula. Or you could find the projection vector and find its length. Either way, or who knows, you might be able to just go in here and go, well, guess what? Actually, I could do this with a little bit of trigonometry, fine, but you still then have to find an angle, which is going to be one of these things. So this is sort of the easiest formula. I never remember it. I always look it up, or I actually just do the projection first. Anyway, so if you want to do a quick example, and then we'll take a break here. For example, find the distance from, I don't know, we use our favorite numbers here. 1 minus 1, 1 to the plane, 2x plus 3y plus z equals 12. So not in standard form, that's okay. Okay, so we have our point. We have a plane down here. We have our point, 1 minus 1, 1. It's a certain distance off of that. And that's what I want to find. So in order to do that in my formula, I need to find point P. I need to find P, and I need to find the normal vector N. So P is any point in the plane, and N is the normal vector. So how do you find P? Well, you find P to be any values x, y, z that satisfy this equation. You can pick anything you want that works. I think often it's easier to set a couple of these things equal to 0 and then find the third one. So if I set x, y, and z to be 0, randomly here, 0 and 0, that means that x would be 6 in order to balance this out. So 6, that'd be 12, 0, 0, I get 12. This point is in the plane. N, well, N is even easier. It's just the numbers in front of x, y, and z form the normal. So we can sort of recognize that. I've got P, I've got N. Go back to my formula for a second. I need PQ. I need the vector for PQ. And then I'll be done here. The vector from P to Q. Well, it's always, what do you have to add to P to get to Q? This is Q. That's the thing. So to get from P to Q, I'm going to have to subtract 5 in the x direction. Go from 6 to 1. I'm going to have to subtract 1 in the y direction. And then I'm going to have to add 1 in the z direction. So go from P to Q. So there's PQ. There's N. And in golden, I know that the distance is just PQ dotted with N, taking the absolute value if I need to.
I just go by Veer, if that makes it easier.
Okay.
Yeah.
I didn't say your name, but that's all right.
VWER. VEER.
Gotcha.
Yeah. Thank you. All right.
So let's see, what do we get here? PQ dot N. So that means I multiply the X components together and I'll get -10. Multiply the Y components together and I get -3. Multiply the Z components together and that'll be +1. And that definitely is negative from my PQ value. And then the length of N. So let's see, length of N is as usual, square, square, square. So 4, 9, and 1, and then take the square root. So that'll be the square root of 14. So my distance will be -13 plus 1, so that's -12. Take the absolute value, 12. So 12 over square root of 14 is the distance away from the plane. So it really just comes down to that formula right there. If you understand what Q is off the plane, P is anything in the plane that is the normal. And that's a good, that's basically the rest that finishes off chapter 10. We do need to talk a little bit about chapter 11, but we're a little bit over where we normally are for break. So take a quick break, maybe till 8:30.
Sure. I have a question before we move on from this.
Yeah, sure.
Maybe I missed it. I don't know. But where did the original P come from? That 600?
This is, the P is any point in the plane.
Okay, so we just came up with that.
Right. And what does it mean to be in the plane? That means that whatever the X, Y, Z coordinates are, they have to be able to, they have to satisfy this equation.
Okay. Okay.
So if we wanted to pick, what's another point that could be in the plane? Well, if X was 0 and Y was 0, then that means that Z would have to be equal to 12. And that would work, 0, 0, 12. So that would be another point. And we can use that. If we worked it through, turns out we would still get 12 over square root of 14 because the top would adjust to end up getting 12 as well. So it doesn't matter which base point. There are infinitely many choices. I just sort of picked the easiest one.
Okay. Thank you, sir.
Yeah. Any other questions on any of those parts or the previous slide before we do our break? All right. Well, I'll see you at 8:30 then, and that's it. See you at 8:30.